Good morning, BC folks. It's Mr. Havenhill, and today we're going to explore alternating series, some absolute convergence, and quite possibly some error theorems as well. And so, buckle up and hold on tight because it's going to get pretty crazy today. So, at the risk of trying to be not so subtle, I just want to emphasize the importance of not just being a spectator versus somebody who's actually doing the exercises here. If you really want to be able to master this material, you've got to do more than just observing and copying notes down and hoping and expecting that you're going to have this material mastered. It just doesn't. Those days of, as I mentioned before, are long gone. You really got to be able to wrestle with this material and really spend some time trying to make sense out of it. And so, with that said, let's go ahead and let's get started. So many of the recent tools we've developed require that a series be a positive series, that is, all the terms are positive, that they're decreasing in order for us to be able to determine convergence. We have the direct comparison test, the integral test, and the limit comparison test, and all three of those comparison tests required those conditions, that a series be positive and decreasing. Well, what do we do for a series that possibly has some negative terms in it? In fact, we lack very effective tools to be able to perform that kind of analysis. And so in this lesson, we're going to explore series that have negative terms. And we're going to begin by looking at series that are known as alternating series. And we've seen these kind of series before. We at least have explored them in terms of their mechanics. But what we haven't had a chance to do is explore whether they converge, diverge, so on and so forth. And so in this particular example, we see the typical behavior of what we know as an alternating series. Remember, mathematicians are not the most creative people on the planet. Our names typically describe exactly what it is that we are working on. And so you'll see here that the first term happens to be positive, the next term is negative, the third term is positive, the fourth term is negative, so on and so forth. The signs of each of the successive terms are alternating between positive and negative. Now, alternating series, they generally come in two flavors. Either all the odd terms are positive, or all the even terms are positive. But in either event, an alternating series has this very characteristic appearance where the signs of each of the successive terms are alternating. Now, it just happens to be that we've got a magnificent test that we can use. I know you're thinking, another test? By the time we're done, we're going to have 10 different tests to be able to determine the convergence of an infinite series. And so we've got a test that we can use to determine whether an alternating series converges or not. And so this is what is known as the alternating series test. Essentially, it says the following. If you have some kind of alternating series, and they always have this particular characteristic where you have -1 to some kind of exponential power. It may be n-1, it might be n, it might be n+1. It's this particular term that's multiplying your series a sub n. This is what forces us to have those alternating signs, positive, negative, so on and so forth. So suppose we've got this particular series. It will be convergent if the following two conditions are met. So an alternating series is going to be convergent if these two conditions are met. First, that the terms are decreasing for every k value. We want to see that the term to the left is always going to be bigger than the term that comes immediately to its right in this particular series. And so we want to see that our terms are decreasing. And number two, we want to see that the limit of the nth term equals 0. And so if we can identify those two conditions, if we can show that the terms of an alternating series are decreasing, and we can show that the nth term is equal to 0, when we evaluate this limit, then we can apply the alternating series test, and we can determine the convergence of an alternating series. So let's go ahead and let's take a look at an example. Does this particular series converge or diverge? Now I'm going to go ahead and give you a moment to write that down, and I'll invite the sub to pause if necessary, and then I'd like to walk you through how to approach this. So I have the same series here written down so that I can annotate it here. And first things first, can we determine whether this is a decreasing series? And so, in other words, can we show that a sub n is greater than or equal to a sub n plus 1? And this is what we're attempting to try to set out to do. And this gets a little confusing because sometimes people get confused by this guy right here. And so let's go ahead and let's just write out a couple terms to see if we can identify what's happening. So a sub 1 would be equal to 1 over the square root of 5. Now some of you might say, wait, huh? Mr. Havenhill, are you sure about that? I mean, look, when we plug in 1 up here, it's not going to be negative 1 over the square root of 5. And if you spotted that, you would be correct. However, keep in mind that the way an alternating series works is you've got negative 1 to the n times a sub n. And so what we are interested in essentially would be the absolute value of each term. What we're looking for is not the value of the sign, but rather the value of the term before it gets multiplied by negative 1. And so in this case, a sub 1 is 1 over the square root of 5. A sub 2 would be equal to 1 over the square root of 6. A sub 3 would be equal to 1 over the square root of 7. And what we clearly have here is the following pattern. We have 1 over the square root of n plus 1 plus 4 is equal to 1 over the square root of n plus 5. This would be a sub n plus 1. That is clearly smaller than 1 over the square root of simply n plus 4, which was our a sub n. So we've got the first condition met. We have that a sub n plus 1 is less than or equal to a sub n. Bam! We've got that guy taken care of. So we have that our terms are in fact decreasing, and we're not being distracted by the fact that we have negative terms. If we were to write this out, I mean, we would have negative 1 over the square root of 5 plus 1 over the square root of 6 minus 1 over the square root of 7 plus 1 over the square root of 8, so on and so forth. And so again, I want to reiterate, because this throws some people off initially. For the way an alternating series is defined, we've got negative 1 to the n power, or n minus 1, n plus 1, some kind of variation of that, times our sequence a sub n. And this is what we're trying to evaluate, not this whole product, just a sub n. Okay, so we've identified that the terms are positive, they're decreasing, and now let's take a look at the nth term. What happens if we allow the limit of n to approach infinity of simply 1 over the square root of n plus 4? And it turns out that that ends up becoming 0. So we've got our two conditions for the alternating series test being met. That's the big if part. If the terms of an alternating series are decreasing, and if the nth term of the sequence is 0, then by the alternating series test, our series is convergent. I'll give you a moment to scribble that down. Example dos. Can we determine whether this particular series converges or diverges? Again, I'll pause to give you a moment to write that down. Okay, so This one might be a little bit more challenging to try to identify, and we could try to list out the individual terms and we can try to spot a pattern, but I want to now encourage you to try something that's a little bit more of a powerful argument, and that's appealing to calculus itself, calculus that we learned last year in AB, to determine whether this thing is essentially decreasing. And what we're going to do is represent this series as a function. And then what we would like to do is analyze the first derivative. And just to kind of recall, when a first derivative is negative, it means the function is decreasing. If the first derivative is positive, it means the function is increasing. And so what we're going to do is represent our sequence here as a function, and then now we can apply our tools of calculus to analyze the behavior of that function. So when we take its derivative, we're going to hopefully try to show that the terms are in fact decreasing. So being that we have a quotient, we're going to imply the quotient rule, and that's low d high minus high d low over low squared. And so we're going to take the derivative of n times our low, 2n squared minus 1, minus the derivative of the bottom times the top over the bottom squared. And when we evaluate that algebraic expression, we end up with the statement negative 2n squared minus 1 all over 2n squared minus 1, that quantity squared. And it turns out that for every single value of n that you choose, this numerator is always going to be negative. And similarly, for every value of n you choose here, this denominator is going to be entirely positive. And so we're stuck with the ratio that is negative divided by a positive, and that will always be negative. As a result, f of n is decreasing, which implies that the terms of our sequence that this function represents must be decreasing. So the terms of this series, if you were to write them out, if this is our a sub n, again, we're not being distracted by the fact that we're going to have some negative terms. The terms of this alternating series are positive, they're decreasing, and so we end up with now the second condition of the alternating series test, which is, can we show that the nth term equals 0? So when we evaluate the limit as n approaches infinity of our sequence, principle of dominance is invoked, and the denominator grows at a much faster rate than the numerator, and the limit is in fact 0. Therefore, by the alternating series test, this series is going to converge. So let's take a look at a few examples rather quickly so we can get a feel for how this thing continues to work. And so here we go. Let's determine the convergence of this particular series. Now, just so that we can kind of see what this series looks like if we were to write it out in terms of its numeric value, for n equals 1, we would have 1 over 1. And then for n equals 2, we would have minus 1/2. And then for n equals 3, we would have plus 1/3. For n equals 4, 4 plus 1 is 5. Negative 1 to the 5th is negative 1 times 1 over, here we go. Okay. Now, when folks look at the terms like this, they get a little distracted because they think to themselves, okay, this one's positive, this one's negative, this one's positive, this one's negative. We are alternating these terms, aren't we, Mr. Havenhill? Yes, we are. But nevertheless, I still submit to you that a sub n is just merely 1 over n. It's not 1 and then negative 1/2 and 1/3. A sub n is simply 1 over n. The reason why this is an alternating series is because we have this additional product out here in front. But the series itself is, in this case, being modeled by 1 over n. So, can we demonstrate that this thing converges or not? And so, if we want to be able to employ the alternating series test, we have two conditions that we need to meet. So let's go ahead and let's take a look at the first one. Is a sub n greater than or equal to a sub n plus 1? How might we show that? Well, a sub n is going to be equal to 1 over n. And how will that compare to 1 over n plus 1, which is what we would describe as our n plus 1 term? Well, for every value of n that you choose, this is always going to be greater than this value here. And so whenever you are dividing 1 by a number that is larger, this ratio will always be smaller than a ratio in which you're trying to divide by a smaller number. And so, so this relationship holds, and therefore the first condition is met. Okay, now what happens when we evaluate the limit as n approaches infinity of a sub n? What will it equal? Well, the limit as n approaches infinity of 1 over n, well, that's 0. And so we have absolutely, for certain, we have these two conditions being met, and therefore, by the alternating series test, our series above converges. All right, let's take a look at another example here before we start getting a little spicier. This one is just to kind of drive home the importance that assumptions do matter. Assumptions matter. So let's determine the convergence of this beautiful looking series. Well, what I want us to do is get in the habit of immediately trying to identify what our a sub n is, which in this case our a sub n is n plus 1 over n. Our a sub n is going to be this guy right here. Again, when we're trying to determine the value of a sub n, we're not paying any attention to this particular term, which is causing our alternating of signs. And so we've got our a sub n, and let's go ahead and let's evaluate the two conditions. Well, condition number 1, can we show that a sub n is greater than or equal to a sub n plus 1? Okay, let's go ahead and let's take a look at that. We have n plus 1 over n. How does that should not be equals, sorry about that. How does that compare to n plus 1 over n plus 1? Now, if any one of you do this, I'm going to bust your fingers up when I return. So this right here we are not allowed to do at all. Now, if you're looking at this and you're trying to figure out how this expression relates to this expression, try plugging in some values for n, and let's see what happens. Let's see what happens when n equals 1. We would have 2 over 1. How does that compare to 3 over 2? Well, that's definitely the case. What happens when n equals 2? Well, we have 3 over 2, and then on this side we're going to have 4 over 3. So we have 1.5 versus 1 1/3. Clearly the sequence on the left is larger. And, well, I'm smelling a pattern. By now I'm pretty convinced that that's going to be the case. So, woohoo! What we have is first condition being met. And you know what? I'm getting really tired. Let's just go ahead and let's move on. Can we just apply the alternating series test, Havenhill? Unfortunately, no, because we absolutely need to double check this step right here. What happens to this limit? If it does not equal 0, then we cannot apply the alternating series test. And so what we've got here then is a sub n, in fact, does not equal 0. A sub n, as n approaches infinity, is equal to 1. Well, at this point, once we've gotten to this stage right here, we could simply apply the nth term test or the divergent test to show that the series must diverge. And it's really as simple as that. Okay, so now what I want to do, and I promise I'm not trying to overload you, I want to try to give you a sufficient number of examples to really feel like you're equipped, but at the same time, I don't want to I don't want to burn you out by giving you 600 examples. So I am going to now kind of transition into a concept that's very related, but it's at the same time it's sufficiently different as well. So let's take a look at this particular series. We want to know whether it converges or diverges. Essentially, we're looking at the cosine of 1 plus the cosine of 2 over 2 squared plus the cosine of 3 over 3 squared plus so on and so forth. This right here, this cosine of n over n squared, that is our series. And we want to know whether it converges or diverges. Well, this is where it gets kind of odd. Some terms are positive because the cosine of 1, it's greater than 0. 1 radian is in the first quadrant. Some are going to be negative. The cosine of 2 is less than 0. The cosine of 3 is less than 0. The cosine of 4 is less than 0 because these guys are all in the second or third quadrant. And so what we have here are positive, negative, negative, and then there's another negative right here, and then it becomes positive and positive again. And so what we have is a series whose terms are sometimes positive, sometimes negative, and it's not alternating. What? Oh, Mr. Havenhill, I can already picture I can hear the pencils being slammed on the desks and the rolling of the eyes and people looking at each other going, oh, is he really doing this to us? Really, Havenhill, come on. Okay, so what are we going to do? Well, one of the keys to understanding a series like this that's not alternating, that still has positive and negative terms, is to study the concept of something known as absolute convergence. Absolute convergence. And so first thing we're going to do is use the basic comparison test, and we're going to take the absolute value of our terms here. Now, technically, I probably should have shown you that I wanted to take the absolute value of the cosine of n over n squared. But hopefully most of you are catching on that the denominator will always be positive anyway, and so suffice it to say that this right here, the absolute value of our numerator over n squared, it's logically equivalent to the absolute value of a sub n. And so let's check to see how the behavior of this thing plays out, and then how it might actually compare to this series up here. Okay, we've seen this kind of comparison before, where we know that the largest possible value of the cosine of n is going to be 1. And so we could say that this value right here, this ratio on the left should be less than or equal to 1 over n squared. Well, this guy right here is a p series greater than 1, so therefore this thing has to converge. And so being that the bigger series converges, it requires the smaller one simultaneously have to converge. So basic comparison test, direct comparison test, they're synonyms for each other. And so what we have here is that the absolute value is convergent, and so we would say that this particular series, I'll define this in a moment, but we would say that it is absolutely convergent. Absolutely convergent. I'll give you a moment to write that down, and then we'll dive into some definitions here. So, since a sub n is absolutely convergent, we would say that it is also simply convergent. Just a sub n is convergent. And some of you might be thinking, okay, what's up with this absolutely business? Is this a different type of convergence? Sort of. Let's go ahead and let's explore what that looks like. So, definition. We would say that A sub n is absolutely convergent if when you take the absolute value of the series, and if you take the sum of all of those absolute values, if that is convergent, then we would say that the series is absolutely convergent. Feel free again, substitute to hit pause for students to have time to copy this down. And we would say that A sub n is conditionally convergent if A sub n is convergent, but the absolute value is not. Mr. Havenhill, you're driving. This is just too much. Some of you are waving the white flag. You'll be just fine. So we have that the series is conditionally convergent if A sub n is convergent, but the absolute value of the series is divergent. And so we've got a really cool theorem that is very much related to these absolutely / conditionally convergent definitions. If a series A sub n is absolutely convergent, then A sub n is convergent. Again, feel free to pause to give students a chance to write this down. So let's explore a couple of examples of conditional and absolute convergence, and I have a feeling many of you will be done after this. So let's go ahead and let's explore. Let's prove that the following series is absolutely convergent. So we've got 1 minus 1 over 2 cubed plus 1 over 3 cubed minus 1 over 4 cubed plus blah, 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 blah. And this is an explicit expression for our series. So how would we show that it's absolutely convergent? Well, let's take the absolute value of each series, or each term of the series, and let's add those up. So we would have 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus blah, 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 plus 1 over n cubed. How does this sum behave? Now go ahead and lean over to the person next to you and ask, can you see it? This is a p-series where p is equal to 3, and therefore this is convergent. And since the absolute value was convergent, the absolute value of A sub n, then we would say that this is absolutely convergent. By now some of you are thinking, oh, Mr. Havenhill, if the absolute value is convergent, then it's absolutely convergent. Ah, ding, 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 ding. If you caught that, well done. Well done. And if you didn't catch that, hopefully you did just now. Here we go. Let's look at example dos. If the alternating harmonic series, or is the alternating harmonic series listed on the screen absolutely convergent, conditionally convergent, or neither? Does it diverge? Well, in order to determine whether it's absolutely convergent or not, let's take a look at the absolute value of the of each term, and let's add it together. Well, we don't have to go too far. We have 1 plus 1/2 plus 1/3 plus 1/4. All that is, we're just looking at 1 over n. And by now we know that that's a harmonic series and it will diverge. Okay, so absolute convergence, whoosh, it's out the window. Now let's check for conditional convergence. Well, that happens to be an alternating series. I wonder if I can apply the alternating series test. So what are my two conditions again? That's right. The first condition is that our terms are decreasing, and the second condition is that my nth term is 0. Well, we clearly have that my terms are decreasing, and then from there we have that the nth term is equal to 0. So sure enough, this particular infinite series is convergent, and so we would call it conditionally convergent. Okay. From here, I'm going to pause because I know that you're probably at the threshold of your pain tolerance. I'd love to be able to give you some more examples, but I have a feeling that some of you are going to snap if I do. And so this recording has been lengthy enough, and I don't want to completely overwhelm you with information. I want to give you sufficient time to start working on some odds at a calc chat, and then compare to calc chat and try to experience some growth. I'm also going to invite you guys to start reading ahead. I have already posted the entire rest of the Larson text for this particular chapter on my site. Please, please, please start reading ahead, especially on the ratio and root tests. You might be wise to start exploring the error that's related to alternating series. And then if you're really, really ambitious, I highly, 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 highly recommend that you start trying to dig into power series and Taylor series, because it's just the more exposure you have to it, the better off you'll be. So if you can find some stuff on Khan Academy or some other kind of site or YouTube, whatever the case might be, if you start exposing yourself to it now, and then combine that with any of the teaching that I have, and then the collaboration we have in your groups, hopefully the combination of all of that will serve you well. So please, I invite you to start trying to expose yourself to some of this content now, because it will feel like a tsunami, and I want you guys to survive. I don't want you to drown. So I'll go ahead and I'll post the assignment I'd like to have you guys work on here next. Okay, here's the assignment I'm going to invite you guys to work on, page 638 through 639, and then the numbers you see on the screen. Now, I'm just going to throw this out there, and I'll let you guys choose. My feelings won't be hurt one way or the other. I do have a couple more examples to show how to walk through absolute versus conditional convergence, and I can walk you through those only if you want to. Now, at this point in time, I can already picture some of you shaking your head going, no, 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 no. But if you want to, I will make that available, and you can play them, or you guys can start working right now. Whatever you feel is going to be the best use of your time is fine by me. Okay, here we go. You asked for it. So here are a few more examples to explore absolute versus conditional convergence. Proceed with extreme caution. Here we go. Let's go ahead and let's take a look at this first Mama Jama right here. We want to determine whether the series are convergent or divergent. And if we do have a convergent series, can we classify whether it's absolute or conditional? So the first thing we're going to explore is this guy right here. Now, I always invite you guys to utilize the nth term test. You should always try to explore this, and in this particular case, we're going to end up with something that actually ends up diverging. You end up with n factorial over 2 to the n, and the top is going to absolutely overwhelm the bottom, and so by the nth term test, this home skillet, it is diverging. Okay, feel free to hit pause after I reveal the next one. Let students kind of work on it, and then we'll compare our results. Okay, go ahead and again hit pause. Let students write it down. Let them work on it, and then in a moment or two, when they're ready, we'll go ahead and hit play. Okay, so first things first. What does the nth term look like here? Well, that's going to approach 0. So the first condition, actually this is condition number 2. This second condition is met. The first condition is a sub n plus 1 less than or equal to a sub n? And in this case, where a sub n is just simply 1 over the square root of n, then we have 1 over the square root of n is going to always be greater than or equal to 1 over the square root of n plus 1. So what we have here is we have a series where we can apply the alternating series test, and therefore it is convergent. But how can we tell whether it is absolutely convergent? Well, in order to do that, we need to examine this. Let's take the sum as n goes from 1 to infinity of the absolute value of a sub n. And so that's just going to be 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3. And this is essentially 1 over n to the 1/2. Well, this particular series, it's a p-series where 1/2 is less than 1, and so therefore this thing is divergent. So what do we call a series where the absolute value is divergent but the series itself is convergent? We call that a conditionally convergent series. Let's go ahead and let's take a look at one more. Again, let me invite the sub to go ahead and hit pause. Okay. Hopefully that was a sufficient amount of time. So let's go ahead and we immediately are noticing the alternating nature of the series. So let's go ahead and let's analyze. We have that the nth term is clearly greater than the term that comes after it. Our terms are decreasing. We essentially have that a sub n is equal to 1 over the natural log of n. And this is going to be greater than 1 over the natural log of n plus 1. So the first condition is met. And what's the limit of a sub n as n approaches infinity? Well, by principle of dominance, you end up clearly with that the limit is equal to 0. So, by the alternating series test, we have that we've got that particular series converges. So now let's determine if this thing converges absolutely or conditionally. This is going to be a little bit trickier, and so we need to try to figure out what we need to do is figure out how the absolute value of a sub n behaves. And that's going to give us 1 over the natural log of 2 plus 1 over the natural log of 3 plus 1 over the natural log of 4 plus 1 over the natural log of 5, so on and so forth. And we're looking at that, and we might initially struggle trying to figure out something to compare this to, because on its own we might not be able to determine how this thing behaves. And so how does this thing be, what can we compare it to? Well, we know that this harmonic series diverges. My question is, how does 1 over n compare to 1 over the natural log of n plus 1 for n starting at 1 going up to infinity? So with your calculators, I'm going to invite you to compare. what is 1 over 1 and how does it compare to 1 over the natural log of 2? Well, I went ahead and calculated 1 over the natural log of 2 and I got 1.4427. And what I have is that this guy is larger. This is for n equals 1. For n equals 2, 1/2, how is that going to compare to 1 over the natural log of 3? Well, it turns out that that's greater too. And so, here's what we have. By the direct comparison test, we have that the absolute value of a sub n must diverge since the series 1 over n, we have that this is less than the series of the absolute value of a sub n. And so since this harmonic series diverges by the direct comparison test, we have that our absolute value of a sub n must diverge as well. Therefore, the series of a sub n is conditionally convergent. I hope you guys have an amazing day.